is going to be Nengkun Yu of Stony Brook University, and he'll be talking about quantum programming, program verification, and testing. So take it away, Nengkun.
Thank you very much. I really appreciate the organizers, Alexandra and Mingshen, for inviting us and inviting me. So I feel very sorry I can't come in person because of my visa issue. So let's get started. So my talk will be quantum program verification and testing. Okay, I will mainly focus on program logic, and it's just focusing more on quantum Hoare logic. So back to 1947, so like John von Neumann initialized the question of classical program analysis, and before that, of course, he's a pioneer of quantum mechanics. So he asked the question of how to test large programs, and then in 1967, so Hoare proposed the Hoare logic and introduced the Hoare triple PS2. And sure, the quantum computing become hot, and people start to think about like quantum program verification, and there are a lot of works. So notably, from my point of view, so we will start from Mingshen's quantum Hoare logic, and then there are quantum applied Hoare logic, which is a simplified version of Mingshen's quantum Hoare logic, and also we have like quantum relational Hoare logic, quantum separation logic, and incorrect logic. So let's first review classical Hoare logic. So the motivation is that for program verification, it's easy to make errors when coding, and when the program is large, the problem becomes very complicated, and also the feelings of programs are very dangerous. So program verification is a task of to prove the correctness of properties of programs. There are lots of approaches. Right? So the deductive proof system, the model checking, type system, abstract interpretation. So a simple classical language is based on like basic expression, Boolean expression, and classical programs. So classical programs consist of like assignment, consequence, and branching, and the while loop. So operational semantics is as this. So we have assertion of predicates as a set of states, and we have Boolean satisfaction, and we write it as sigma satisfy p, so sigma p. So the basic expression, we can understand that if it's an expression, so and also the sequence is first S1 S2 sigma, first apply S1 and execute S1, and then try to execute S2. And the case is when the system, the current state satisfies the Boolean variable b, then we go to the first branch C1, otherwise we go to the second branch C2. And the while loop is that whenever the Boolean the loop guard is satisfied, we go to the loop body, and if it's not, then we jump over the loop. So the validity of the Hoare triple is consists of two definitions. First is called partial correctness, which is defined as partial PCQ. So C is the program. So it holds if for any sigma, the current state in input state sigma satisfy P, then after the execution, the output will satisfy Q, or the program will abort. And total correctness is denoted by total PCQ. So it holds if for any sigma, if sigma satisfies P, then output will satisfy Q. So it guarantees, the difference is it guarantees the termination. So our goal, or the goal of Hoare triple, is to check the validity for any given Hoare triple PQ. So this was done by deductive reference rules rather than semantics. So this is the very famous inference rules. We have like axiom, sequence, consequence, case, and loop. So the Hoare logic is very powerful because it's sound and complete. For sound, we mean that for any derivable triple is valid, and the completeness is that any valid triple is derivable. So this motivates us to consider what is Hoare logic for quantum programs, how to understand quantum program states and assertions, how to define syntax, semantics, how to explain the validity of quantum Hoare triple, and how to design a sound and complete proof system. So this part will review the Minsheng's paper, Floyd Hoare logic for quantum programs. So different from classical quantum states considering qubits rather than bits, and the initialization or the assignment is not assigned a variable to a value, but assigned to a quantum state. And operation of quantum states is no longer plus, minus, multiplication, and arithmetic operations, but instead it become like unitary and quantum measurement. So in Minsheng's quantum Hoare logic, the quantum assertion is given as a operator, unobservable, where all eigenvalues lies in the interval 0 and 1. So the satisfaction is denoted as trace and row, denoted the degree to which the state row satisfy M. So it's continuous. It's not Boolean. So different. So for you can see the table. So deterministically, the state is X, the predicate is P, and satisfaction is S. Satisfaction. For probabilistic, our state is a distribution, and our predicate is a measurable functions, and the expected value is the integration. And for quantum, we focus on density matrices as states, and our predicates as observables, and satisfaction we consider as quantum expectation value. We can also consider the syntax of quantum programs or quantum wild programs. So we have like initialization. We initial the quantum register Q into 0, and we apply U on this quantum register and perform measurement. And a slightly different part is the if. So if in classical is that for any given state you only have like it satisfy B or not satisfy B, right? It's Boolean, and also as well as Y. But for quantum, we actually in imaginary we apply a measurement M, and measurement not return a distribution, but return a Boolean value which a base distribution defined by quantum mechanics. So does the Y. Then based on the outcome, we become that is a Boolean or integer or classical value. We go to different branches or loop body. So the operational semantics is as this. So the basic expression, if we initialize Q into 0 and row, then we initialize the register of Q into 0, but leave the rest registers in row untouched. We apply unitary, so we apply U row U star. This is because of the positivity of quantum mechanics. So if we only care about pure state, then we only need to apply U state. We don't need to consider that. And the case is also similar. Expect after the measurement they will collapse. We also have the loop version. So just remember, at any time if we perform a measurement, then the measurement will collapse the state into different states. And the denotational semantics is like for any program S and any state row. So the execution of S on row returns out the value as a summation of the multiset of all possible outcomes. This is a well-defined semantics because trace row is smaller than 1, then all the output, the trace of S row is always no bigger than 1. Okay, let's take a very simple example. So well-known quantum teleportation circuits. So what do we mean by teleportation? So suppose we have a Q0 state, let's say it's from New York, and we want to send this state to someone in Copenhagen. And the communication is very noisy. So what we do, the interpretation is that if Copenhagen and New York shares the maximum entangled state, let's denote as beta 0, 0. Then from my side, I can perform a measurement and just send classical information to Copenhagen to recover the state. So program is like this. And so S1 is like we apply Q0, Q1 in the C naught, and then S2 is like we apply Q1 an H gate and we perform measurement. Okay, so operational semantics, when this psi is 0, so the execution we get that the other state Q2 at Copenhagen becomes 0. And if the state Q0 is 1, so after the execution, the state in Q2 is also will also become 1. So the validity of quantum Hoare triple we defined Ming-Shen defined as follows. So the first correctness is P row less than trace QS row. So comparing with the classical horology formula, so if the input satisfies P, the output S satisfies Q. Okay. And for partial correctness, we denoted as also denoted as partial PSQ. So which is holds if for any row trace P row more than trace QS row plus trace row minus trace S row. So you can see the last part, the trace row minus trace S row, is just to denote the probability of non-terminated row. And we can so Ming-Shen developed the quantum Hoare logic proof system. So which we have like initialization and we have unitary operation. And also the sequence rule, the consequence rule. And here we use loop no order operators because we are semi-definite Hermitian matrix with positive eigenvalue. We call P prime smaller than P if P minus P prime is positive. So this is a case rule. It's very similar to classical, but slightly different in the sense that we have to take into account that after for the case rule and the while rule, we have to perform measurement for program branching. But when we perform measurements, they will collapse. So here we have like the precondition of the right hand side. You can see it will be normalization M over M dagger PM M. So this denotes as after the measurement. And the loop rule is more complicated. So you can see classical loop rule is B and P on C1 after C1 satisfy Q, and negation of B and P after C2 satisfy Q. Then we have P while Q. But for the quantum loop rule, we have to change a lot of things. In the sense, first is like a probabilistic combination, and also we have like a class of state after measurement. So the condition will become like a P M0 star Q M0 plus M1 star P M1 after the while loop will satisfy Q. And this is for partial correctness. If we want to total correctness, Ming-Shen introduced the bound function. Okay, so the proof system is perfect in the sense that it's sound and complete. But observable are kind of counterintuitive. And actually for classical mind of our classical mind of program analysis. So we familiar much more with the Boolean variables or regard or K as Boolean function. So then we talk about like projective quantum predictors. In the sense that this is easier. And also we observe that the general measurement and the projective measurements have the same expressive as long as we introduce ancillary system. And also for application purpose, most existing quantum algorithms are related to pure space. So for projections, the satisfaction is a Boolean function, and we can define projection-based assertion, and which has simplified proof rules. Okay, so we know that for any quantum program or quantum one program, the termination space, which means that considering every projection corresponds to a space. So this is very natural. And we have some rules for projection, and we have the logical operations. Very simple classical Boolean variables. The only thing is that we define as the span of P and Q for two subspace, two projections P and Q. And this also very similar, and the total correctness very similar as the logic. And further, we have the relation with quantum. So here we denote as A. A means that is applied quantum Hoare logic. So we have the lifting. So if for program, so if applied quantum Hoare triple is valid, then the corresponding quantum Hoare triple is valid, and vice versa, as long as P and Q are projections. And we also have the reduction. So this is comparably, we have a much simplified rules, because you can see here from the left-hand side, we come from summation of dagger PM. We went to like the Boolean operators, the measure and the projections. Okay. And we can also use the bound function. So for this applied quantum Hoare logic, we also have like sound and completeness rule. So we can use this to verify HHL. There are many follow-up and corresponding works of quantum logics. So you can use the incomplete of the first part, the follow-up work of quantum Hoare logic, and first several are not. So these are the references we have now. So then I want to talk about the quantum incorrectness logic, because the verification purpose is to notify errors. Right? So this was based on the incorrectness logic and my work on quantum. So it is in quantum programs. So there are lots of examples, and to make the absence of bugs in quantum programs, there are lots of efforts. So how to find bugs if there is one, or they are there already. So let's consider for classically Peter O'Hare introduced the classical incorrectness. And in my Uppsala 20 paper, we have a dynamic assertions. I'll talk later. And in Huang and Martinossi, for statistic assertions. And Ken has a tree. So we want to introduce bug finding ahead of runtime. So the first is classical, but for the second, it does not. Is a testing, and for statistic version, 19 paper, it's not. We did not find a soundness or uncompleteness argument. And for the automata, we don't have a proof system. So for my expertise, we want to extend Peter O'Hare's paper from classical incorrectness to quantum incorrectness. So let's first recall the classical incorrectness logic. Otherwise, you have approximation and the incorrectness logic, the approximation. So in some sense, they satisfy a duality relations. So for so the logic is defined as P as Q. So every state is in Q is reachable from some state is in P. And so we have to define a quantum program correctness. We have to extend we have to extend In's quantum Hoare logic to add errors and assert statement. So for simplicity, we consider assert as a projection. So for instance, if rho satisfies P, then we assert Q, P will pass a certainty without collapsing rho. And if rho is not in P, so assert Q, P will turn rho into P rho Q or abort abnormally. Okay. So we add one semantic error rho, error, then we will abort. Okay. So whenever we find an error, so we abort. So we can define similarly as a denotational semantics. And we have this symbol. So if rho C is 0, rho E is 1, and rho is 0, 0 plus 1, 1, so we know that rho C satisfies PC. But no predicate QE such that rho satisfies QE without bringing false positive. So the solution is we provide an under approximation relation. So we say like this. So if rho bigger than P in the sense that the support of rho contains P. So we have further examples to say we assert Q is 1. It as most has two output, like 0, 0, 1, 1 in a sense. So the state under approximation by Q is like all rho such that rho can be written as P0, 0 plus 1 minus P1, 1 for any P is greater than 0. So we can also provide a solution as a mixture of reachable states. In the sense that if it achieves P, the mixture of states as achieves Q. Okay? And achieve Q means that it's possible to enter the false range. So we can put the solution 1, 2 together. We define the assertion as a Boolean assertion. And with no false positive and with quantum reachability. And the validity is that for any program, the correctness form of PS Q holds if for any rho that P summation, so the output of S rho Q for if is okay or error. Okay, so here this output is just the semantics. Okay, we define the duality between this formula and the applied quantum Hoare logic, and we introduce the proof rules. And this is a branching structure, and this is a assertion. So OK is support RP R dagger, and Q error is support R perp, meaning that also complement of R P R perp dagger. Okay, so then we denote that the P assert Q bar R is OK Q OK or Q error, in the sense that because we imaginary apply the when we do the assertion we apply the measurement. So if we return OK, the state will collapse to Q OK. If we return to error, the state will collapse to Q error. So we prove boundness and completeness. And also we can bound the iterations of the loops for completeness. And this is an application to of our logic. Okay? We still do it for application. Okay, these are further readings for quantum bugs. Okay. In this part, I will talk about quantum relational Hoare logic. This is based on the work in POP20 and CAVE24. So relational Hoare logic is introduced to verify the relational property. So two programs C1 and C2. So input C1 is sigma 1, input of C2 is sigma 2, which the jointly they satisfy property, let's say phi. Then we want to say that the output will satisfy psi. So we have applications in crypto proofs and differential privacy and expected sensitivity. So probabilistically, we have to work on probabilistic coupling, and we can also have probabilistic lifting. And the correctness of the relational Hoare logic is that if for all sigma 1 and sigma 2, sigma 1 phi sigma 2, meaning that the input jointly phi sigma 1 sigma 2 satisfy phi, then the output will be able to lift to satisfy psi. Okay. So to define quantum coupling, so we move from probabilistic distributions to density matrix, and the binary to Hermitian trace, marginal distribution to partial trace. Okay, so partial trace is very common in quantum mechanics. So we give two density states, rho 1 and rho 2, so we can define a coupling of rho 1 and rho 2 on the joint space is like if trace 1 rho equals rho 2 and trace 2 rho equals rho 1. And we can define things, so if rho 1 rho is density matrix and rho over H1 tensor H2 witness of the lifting. And the correspond to a subspace is like support rho lies in the subspace X. Okay. So we can have like identity relation, symmetric subspace. This is slightly different from classical because identity is like just the A. The equivalent is the can use it to talk about U1 equals U2 or ρ1 equals ρ2. Okay. So the validity for projective predicates we can define this way. So ρ1 A star ρ2 can introduce us to S1 ρ1 S2 ρ2 and to B. And we can also have like for Hermitian predicates. So this is the extension of quantum Hoare logic rule to relational rule. And we also need to have the measurement to synchronize the execution. Skip this part. And we do use the circuit for quantum prediction to see, yeah, it's correct. And then we introduce the approximate quantum coupling. So for two given density states, rho 1 and rho 2, so we say rho is a delta coupling. So if the difference between the partial trace and rho of rho and the rho 1, rho 2 are very small. We can also define the approximate lifting. And there's an approximate equivalent saying that if rho 1 and rho 2 are approximately equal with parameter delta, then the distance between sigma rho 1 and rho 2 is smaller than 2 delta. And we can define the validity for approximate quantum relational Hoare logic judgment. So rho 1 A star rho 2. So we insist that the input will be perfect, right? And the output is like can have like a delta difference. And we also need to introduce approximate measurement conditions. So we have some modified simple rules. You can see we take the example of the first one. So if S1 and S2 one relation from A to R, S1 prime two are related with R to B. So S1 composite with S1 prime is delta 1 plus delta 2. S1 relation S2 S prime. So this is the multi-dimension rules. So we use approximate quantum relational Hoare logic to reason about approximate quantum Fourier transform. So these are further readings of the quantum Hoare logic. So now I come to the last part. It's called quantum program test. So mostly from my work on Uppsala 20 and this ASM paper. Very short. Okay. So we talked about verification. So verification was for understand the program is correct without executing in a real quantum computer, because the quantum computer is very noisy. So, but usually verification can maybe provide a trade-off. So if we want to run applied quantum Hoare logic or even mean quantum Hoare logic, we need relatively large computational power in classical computer. So although verification is able to guarantee the correctness, it's really very expensive. Testing is cheaper in the sense that it can remove many assumption errors, although not guaranteed correctness. So in particular, current quantum machine, so it's very noisy. So and would be encounter lots of errors. So testing will be able to help us to recover lots of errors, while verification will always generally give you like it's not correct. So as we discussed, so we talk about times and times. So you can see here we use projections to test quantum state. So first, it has small expressive power. In that we are not saying that this state exists. Or yeah, I can see it. We want to add some level of information, and introduce efficient checking, because the predicates satisfactory can be checked with not of many executions. Okay. So you can see this diagram. So you can see here. Suppose your state is at rho, and your correct subspace is at P. And if we perform a measurement, in the sense that testing, we run it on a quantum machine. So in case we obtain result P, that is in the correct subspace, right? And the state collapse to 0. Okay. And also, there's a possibility it will collapse to a wrong subspace, also subspace of P, and the state will collapse to P of rho P per, as our incorrect logic denoted. So what's the good news is that if your state is very far from lies in the subspace P, my measurement will, with very high probability, get you to make a mistake. Otherwise, you will go to the correct subspace. So what's the good of this? So after my execution of this command, let's say like a while loop or a branching statement, whatever the current state is, as long as it collapsed to the correct state, in the sense I did not find any error, and in the next round I find an error, I can guarantee that the next round of program must test me, because you can see, as long as I pass the current test, my state already satisfies the things I want. So it will help to locate the error. Of course, so for testing, many executions without seeing errors does not mean correctness. It's just that we just not to observe. It's just to say that let's say we see the sun is rising today, does not mean that it will rise tomorrow, because but we're able to claim it it will rise tomorrow with some high confidence, right? So in the sense that we have to deal with quantum program testing, we have to deal with statistics, just like quantum mechanics. So these are the further results. For me, there are many interesting papers of quantum program analysis recently, and yeah, I list a very incomplete list. And thank you. So I'm happy to answer any question and see your comments.
Thank you, Nengkun. You forget that we're in Copenhagen in the summer, so the sun doesn't seem to rise inside at all. We started a bit late, so we have a few minutes for questions. I'm going to take the first one.
Sure.
On an early slide, you referenced you don't have to go back to it, but the quantum predicates that Ming-Cheng Ying used in his first quantum Hoare logic paper are based on what are called are based on expectations, right? And that was based on a work by Elie de Haan and Godin that argued that those are really the right way to think about quantum predicates as these Hermitian operators that correspond to the to expectations, in the same way that Dexter-Kozin argued something like 30 years earlier in the early 1980s that you needed expectations to reason about probabilistic programs. So, and he seems to have been borne out right in the probabilistic domain. So I just wanted to ask, kind of like, there seems to be there are a bunch of papers going back and forth on that, and from my perspective, it seems like, you know, Shor's algorithm, Grover's algorithm, a lot of these are probabilistic, and I'm kind of inclined to believe that Ming-Cheng was right to begin with. So can you say a little bit about the practicality of the two different approaches in the quantum setting?
So it's the difference between those and projections, right?
Yes.
Yeah. So exactly. So observables. Oh, sorry. Let me go back to that. So observables enable us to understand the acceptance probability of the an algorithm, and the projections advantage is easier. So you're absolutely right in the sense that yes, observables enable us to track groove search and also track Shor's algorithm. But if you can see, I read Ming-Cheng's paper many times and find that for simpler use, theoretically, of course, observable is fantastic. But for application use, Ming-Cheng's example was Grover search with which will terminate with certainty. So simplification will help for further applications. I mean, programming. So on the other hand, although like Shor's algorithm is probabilistic, but some part of it is actually deterministic. For instance, quantum Fourier transform, you can actually reason with projections because it's totally unitary. And you can even simplify your reasoning by considering the structure of quantum Fourier transform. So I'm not saying that projection can replace observables, but it can simplify lots of steps in the middle. So possibly at some point we want to reason about some quantum program at some place or multiple places. I'm just using projections, which is strong enough for me to get enough important information. And then at some point I leave it relaxing it to observable to be reason about the general acceptance probability. This is one thing. The second thing is that, sure, we want to reason about probability, but general quantum programs or general quantum algorithm we don't intend to understand a probability distribution of the output. We only want to get the right result. In the sense that we only require that the output will satisfy some property with high probability. This provides some relaxation of using projections. So if we use projection, and we can introduce a noisy parameter, just like the approximate quantum relational Hoare logic I did. So as long as I can reason that, yeah, I don't know the algorithm, I'm not sure whether the algorithm will accept with probably, let's say, 99%. But I know that the acceptance probability is greater than, let's say, 98%. So I can bound the error probability to like 2%, and that's enough for me generally. I hope that.
Yeah, thanks for the very clear answer. So one more question from Jensen.
Hello. I wonder where you are with the mechanization of these logics. I mean, one of the reasons for the success of Hoare logic is that we now have the tools for mechanizing it, the classical one, I say. So where are you with mechanizing the proofs?
I suppose you're talking about tools, right, for implementing the Hoare logics, right?
That was a yes.
Hello? Oh, the mission has a paper in case, I think 2 years ago, which support the implemented the tools for the quantum Hoare logic. So there is so it's automated already.
Thank you. All right. So our next speaker.
Thank you very much. Let me share.